Okay guys, it's time to finally do the alignment on this radio. I've got the radio turned on. We'll do another alignment. We did one before and yet there were some weak tubes and some other things wrong that I should have known about but wasn't aware of. So I'm going to go ahead and do it again now to make it right.
Let's get set up, okay?
Okay, 0.1 microfarad capacitor. That's going to be the dummy antenna. We're going to connect the high side to terminal 1 of the antenna terminal board. Low side to chassis. Okay, we want to start with the thing fully closed, the tuning condenser fully closed.
With it fully closed, the dial needle should be 2 3/16 inches from the left side of the dial.
Of course, I'm going to convert that to millimeters. This inches thing is for the birds, man. I'm as all-American as anything, but you know, better is better, and the SI system is better. Period. So let me do that. There's, in every inch, there are 25.4 millimeters. So let me break out my very vintage, original Hewlett-Packard HP 15C scientific calculator. This is what I used in college back in the early 80s. This is the very one. 2 3/16, 2, enter, 3, enter, 16, divide, plus. It's 2.19. Okay, inches. There's 25.4 millimeters in every inch. So we're going to multiply that by 25.4. 25.4 times 55.56 millimeters, essentially 56 millimeters for as close as I can get. I want 56 millimeters, okay, from the left edge of the light bracket. So here is the left edge of the light bracket. 50, I was pretty darn close. So essentially it's 56 millimeters. That's pretty good. All right. We used to say when I worked at the power plant, that's good enough for government work. I'm going to go ahead and connect this up now and put 455 kilohertz into the radio after I reconnect the ground. Okay, volume is full on. Frequency generator is going to be down kind of low, at least to start. Connector up right here. All right, let me turn the signal generator down. Oh, I did forget. I need an output meter. My output meter is this, I like to use this Philco 87 Mark III, and it works just great for this kind of thing. I don't need a vacuum tube voltmeter. I don't care what you say. I don't need one. I'm not going to use one. Hate using them. They're a pain in the butt. You can use one if you like, if that's your thing. All right. Was that pretty clear, or do I need to say that again? There we go. It's upside down, but I think we can live with it, right? Okay, the first place you connect the output meter is from number 3 terminal on the antenna strip across to ground on the chassis. Okay, so terminal number 3, it goes 1, 2, 3, okay? Okay, so anyway, let's turn this back on. Okay, it's about 17.5 millivolts. Great. A1, A2, A3, and A4. I marked these earlier when I was doing the alignment before. There's A1, there's A2, there's A3, and there is A4. So let's hit A1 first. Okay, you always want to do the one farthest away from the RF section first, the one closest to the output. As you improve the alignment, the radio will get louder. Keep turning the volume down to avoid the automatic volume control from messing with your readings, because it'll tend to turn the radio down. Now we're going to couple to the loop. Wires everywhere. You can tell I'm tired. It's about 10:30 at night right now, and I'm an early morning person. I'm not a late night person. Okay, now we got some signal coupling. That's good. Now we need to put this on shortwave. Okay, and this needs to be 8 3/8 inches. Okay, so what is 8 3/8 inches? 212.73 millimeters, so about 213 millimeters. Okay, there's 210 and 220. 213 is right about there. Yep, there we go. Okay. 15 megacycles. So I'm adjusting A5 for maximum output first. Alright guys, I can hear all the mouse clicks as you're all moving on to other videos. I don't want to bore you to death. That's A5. So what I'm going to do from here on out, A8 is the next one over, is just kind of point out some highlights. I'll show you where a few of the trimmers are and I'll go right over the highlights, and that's about all I'm going to do. Alright, that one over there is A6 and A9. Alrighty. Now let's try, let's disconnect all this stuff and see how the AM is performing, okay? Let's turn the volume down. Let's just turn this on and see what happens.
It could be anything from... And this is what it sounds like when real people learn in Chevy with the silver. Causing almost immediate harm.
Oh, no. So the little darling bought his mother a present.
Now we have the AM. Let's get ready to start the FM. We'll start that in just a minute. So to do the FM, the first step is to connect the signal generator to pin number 1 of the 6BA6, which is right here, and the other side to the chassis, okay? In order to make that happen, I've got to tilt the chassis. 9.1 megacycles, tuning cap fully closed. So that, I think that's the IF for that. Tuning cap fully closed. Radio's turned all the way up. Let's see what happens here. All right, perfect. Okay, right now I'm trying to adjust the FM. I've got it tuned to the FM intermediate frequency of 9.1 megahertz.
Long story short.
Hey guys, can you believe it? That's FM. Check it out.
You'll be the same respected ASU degree as on-campus student.
Brought torrential rain and winds of about 140 kilometers an hour along the Gulf Coast of the United States.
Soaring, lay your head on my heart.
KRCL, Salt Lake City.
All right, now you can kind of hear how it sounds after the FM alignment is done. I actually went back and did a couple more passes on a couple of the adjustments and got it a lot nicer. But I think I've shown enough of this. This is real grunt work, especially on this radio. This radio is a bear to work on. So I'm going to move on now. We have other things we need to cover. All right, so let's get to it. What do you think, guys? You think Buster wants something? What do you think Buster wants? All right, now that I have both the AM and the FM working, I want to figure out why it is that the transformer is running so hot all the time. I'm a little concerned about that. I knew I'd have to address it at some point, so it's time now to do that addressing. What I've done is I've gone ahead and taken the fuse out. This should be 320 volts AC up here at 4 and 6, and these should be 310 volts DC at 8 and 2. Okay, looking at the chart that's given, the voltage reading chart that's given with the schematic, here are the measurements I should be seeing. Of course, I'm going to start with the 5Y3, but I'm going to go through and check all of these. But I am guessing that with that transformer being hot, that I have about 124 volts going in versus the 117 test voltage that these numbers were developed from. And I want to be a lot closer to the 117. I'm pretty sure I'm going to see that these are high, that this AC voltage is high, and correspondingly the DC voltages will also be high. If they are high like I expect, then I have an idea for what I'm going to do to fix that. And just kind of watch along and you'll see what we come up with, okay? Okay, it's really tough to see in here where I'm going to be measuring, so I'm not going to really try to show you, because that rectifier is buried down in there, and I'm around high voltage, and the last thing I want is the camera to be distracting me or causing me trouble. So I'm just going to leave the camera way back there, and we're going to have to live with that. If you'll keep your eyes on the voltmeter, that'll be your job, and I'll stick the probe in the different places that it needs to be. So we'll kind of work together on this, all right? I took the fuse holder out, as I mentioned, so I jumpered across the fuse with these gator wires. But these gator wires enable me to insert a resistor in here if I do get high voltage on coming from that main power transformer. So let me just see what I get. I'm going to look at the various measurements on the rectifier tube with it just without any adjustments, and maybe we won't need any adjustments. Who knows? Let me turn on the juice. Okay, power is on. Okay, 124, 125. I don't need the radio playing, so I'll turn that down. Like I said, your job is going to be to watch this multimeter. The 5Y3, I'm going to go to pin 2 now. 310 volts DC is what I should be seeing. So let's go to pin 2. Let me get on my good glasses because I need to be able to see what I'm doing. You know, I could misplace. My mother used to say you'd lose your head if it wasn't attached. And she was right. Alright, we're going to look at pin 2 of the 5Y3. And like I said, I want you to watch the meter, and I'm going to mess around with the tube here, okay? So here we go, pin 2. What the heck? Oh, it helps if I have the ground connected to chassis, which is what's supposed to be the case. 350.2 volts, alright? 350 volts. What am I supposed to have? I'm supposed to have 310 volts DC. That's already bad. I'm 40 volts over. We know that's not good. So obviously pin 8 is going to be the same, but let me go ahead and check it just for grins. Okay, there we go, 349.5, essentially 350 volts. Okay, so we know we're in bad shape there. Let's check the AC on pins 4 and 6, okay. AC. Now getting down to pin 4 is a trick on this, so just bear with me. 344.2 volts on pin 4. Pin 4 is supposed to have 320 volts, so we are about almost 25 volts high on pin 4 in AC. Now pin 6, 344.5. Okay, so we're almost 25 volts high on AC. Immediately we know we're high, okay? So we know we got some adjusting to do. But what for the hell of it, let's go ahead and look at the plate voltages for the 6V6 tubes, okay? So pin 3 is correct on the 6V6s. Alright, so 1, 2, 3, yikes. 271 volts is what I'm seeing. I'm supposed to be seeing 240 volts, so I'm about almost 32 volts high on the first 6V6. I imagine it'll be the same on the other one. Alright, 271 volts. So I'm 31 volts high on the plate voltage of the 6V6. It's definitely, that's a big part of the reason why the transformer's hot. So let me go ahead and tinker around with making an adjustment. Now the way to make an adjustment to these voltages, since they're high coming in to the rectifier tube, if they're high coming out of the secondary, they're high going in. And we know that they're high going in because it was these numbers were developed from using 117 volts as the line voltage, but now they're 124, 125 volts. So what we need to do is bring them back down. Do we need to bring them exactly to 117? No, we just need to bring them close, okay? We need to make it better. Right now, we're way high, and we need to make it better. But I don't really, how do I pick out, you know, what resistor to use? Obviously, I need to use a power resistor, and I like to use something like these right here. These power resistors are real handy. They're in a nice metal package that have screw holes, so I don't have to worry about mounting them to a terminal strip or anything like that. I can just drill a couple holes. I've actually made myself a cardboard template so that I can mark the holes and drill them and be done in one shot. I go ahead and mount these on, because they're a metal case and they're a ceramic. It's a wire wound resistor, I believe, with a ceramic envelope around it, and then it's encased in this metal package. Because it's a metal package, it dissipates the heat really quickly, and that's really nice. And if you're smart and you mount this right up against the chassis, this will take care of heat. Now I try to keep these outside the chassis, okay, not inside. The trouble is now I've got to bring line voltage out to this thing and make sure some curious, snot-nosed kid doesn't get his hands in there and start messing around and touch one of those. So that's the trick, okay? But if I put it inside, then it's had an awful lot of, because these dissipate a lot of heat. It adds an awful lot of heat to the underside of this thing, and that's going to cause problems with, transformers already dealing with heat, with capacitors, and we've got ceramic capacitors in there that don't like changes in temperature. I got to warn the owner, of course, of two things. Don't touch these, right? Keep your kids' hands out of there. The other problem with these is that they get really hot. And they get hot enough to burn you to touch them. So you want to keep kids' hands off of these too, and actually anybody's, adults' hands too. If you're a curious type of person, you start, if the way you find out about the world is to touch everything, well, you're going to burn your fingers touching that, because these get hot. Right now I have three varieties of these. I have a 25 ohm 25 watt, which I suspect is going to be the right one. I have a 50 ohm 25 watt, and I have a 100 ohm 25 watt. Now I really think it's going to just need the 25 ohms, but let me go ahead and plug in this 100 ohm and see what happens. Now it's 100 ohm 25 watt, so it maybe get real hot real fast and maybe too much for this resistor, so I will leave it only on for a minute if the numbers aren't right. Okay guys, so let me go ahead and show you what I'm going to do to put it in line. I told you I jumpered around the fuse, took the fuse out and jumpered around it. So now I have, this is basically breaking the line cord that comes into the radio. So connect it to one side, connect it to the other side. Now I'm going to want to measure the voltage drop across that resistor, because that'll tell me that and the current that I'm passing, which I'm measuring over there on my Variac. That voltage drop and the current, and I'll just tell you what the current is so I don't have to move the camera, will tell me just how much power I'm dissipating, okay? So let me get my ohm meter here connected across this resistor so I can measure voltage. Now I'm going to be measuring AC voltage, of course. So I'm going to be that resistance is going to be based on that AC voltage. So that means that it is not an entirely perfect calculation, right? Because I'm not really accounting for the reactive part of the AC voltage, but I'm measuring voltage across just the simple resistor. So I don't know, there will be somebody that will holler at me that I did it wrong, blah blah blah. This will be close enough to get me in the ballpark of what resistor I need. All right. Yeah, I'm an engineer and I understand there's more to it than that, but I also understand it has very little to do with the reality of what I'm going to be doing here. Alright, so we see the voltage drop across it right now is basically 5 millivolts. Let's turn it on. As we start to move current through this thing, we'll start to see voltage drop. Okay, that voltage drop is 47.9 volts. That's a big drop, guys. That's going to be way too big. Okay? That's going to be way too big. Let me, ooh, it got hot really fast. But what the hell, I'm already there. Alright, let me go ahead and measure those DC and AC voltages on the rectifier only, okay? So right now I want to measure on pin 2, I'm looking for 310 volts DC. What do I got? 212, way too low. Alright, I'm not even going to measure pin 6, okay, or pin 8. I don't need to. Let me measure pin 4. I'm looking for AC, okay? So now I'm going to measure pin 4. I'm looking for AC volts. I'm looking for 320. Let's see what I get. 221, way too low. What that's telling me is that resistor is dropping the voltage way too low. And yeah, it's hot. It's really hot. Holy crap, I can't even hold it. That's not going to work. Alright, that's obvious that's not going to work. So, let's go ahead and put in this 25 ohm, okay? First things first, let's measure the voltage drop across the 25 ohm resistor so we know. So, let me go ahead and put this on the resistor. My setup's not exactly the most scientific looking setup in the world. Okay, we're going to look at AC voltage drop across that resistor again. That's not exactly the same as what we're trying to accomplish, but alright, what are we dropping here? Okay guys, that's much more reasonable. We've dropped 17.5 going on 18 volts. Okay, coming up to 18 volts as it begins to pull more current. So roughly 18 volts of AC drop across that resistor, okay? I can live with that, I think. Yeah, it's not really warm. It's not cold anymore, but it's not warm. Alright, so let's go ahead and measure our voltages at the rectifier. Let's see how we do. Alright, so we're looking for DC volts at pin 2 of 310 volts DC. Let's see what we get. Alright, basically 300 volts. So we're 10 volts shy. Can I live with 10 volts shy? It's a hell of a lot better than 40 volts high. Let's see if we got sound. Oops. Yep. Yep. Remember, my lights are noisy as hell. Okay, so we got 300 volts. Let me check it one more time. Yeah, just shy of 300 volts. Okay, I can live with that. Let's check at pin 4 for AC voltage, okay? Boy, it's tough to get down there, so I'm just going to check pin 4. I'm not going to check pin 6. I don't need to. They'll be the same. There we go, 300 volts. Okay, 300 volts AC. Alright, so let me check one more time here. Pin 2. Yikes. Alright, heading down to pin 4. We're looking for 320 volts AC. Let's see what we get here. We're getting 300 volts AC. So we're 20 volts shy. Yeah, okay. Alright, so can live with that. Let's see. So what we have, I'm not going to try and measure pin 6. It's too hard to get to. We have dropped 20 volts in AC. Alright, we're 20 volts short in AC on pins 4 and pin 6. And we are 10 volts short on DC voltage. So that's going to affect B+. That DC voltage is going to affect B+. B+ is going to be a little bit shy. Not terrible. It's going to be a little shy. So let's look at the plate voltage across the two output tubes. Okay, they're easy to get to. That's pins. That's going to be pin 3 of the two 6v6s, which are right here. That's easy to get to. Okay, pin 3 of the 6v6. Number 1 is 233 volts, and I am expecting to see 240 volts. Hey, that's not bad. We're 7 volts shy. I can live with that. Alright, let's go down here. 1, 2, 3, pin 3. Alright, 233 volts essentially. So we're about 7 volts shy on plate voltage for those two outputs, which is really what's going to matter. Let's look at, just for giggles, let's look at another tube. Let's look at that 7x7 tube, okay? Okay, here's the 7x7. This is the driver tube for the two 6V6s, okay? That's an important one too. I'm going to look at the plate voltage for the triode. We're going to ignore these diodes right now. We're just going to look at this triode that drives the two 6V6s, okay? It goes through a resistor, this 220k ohm resistor, so it's not going to be the same as what you'd see across these 6V6s. It's going to be lower, so let me see what it should be. The 7x7, and that's going to be pin 2. 7x7 pin 2 is supposed to be 120 volts DC. So let's see what we get here. 120 volts DC. 114.4. So we're about 5 volts short. I think this is good. I want to look at one more thing. Okay, I want to look at pin 6 of the 7x7 because I was having trouble with the voltage measurement during the alignment across this capacitor right here. They call it capacitor 12 in SAMs. So let me measure that. That should be a negative number because this electrolytic capacitor is on backwards. In other words, the positive of the electrolytic is connected to ground, which means that this should be negative. And that makes sense. This should be a negative number right here. It's basically collecting electrons and bleed them off through this resistor here. Let me measure that. Pin 6 of the 7x7. Okay, negative 1.7. So I'm looking now at pin 6, and that is where the negative of this electrolytic is, and I'm seeing negative 1.7. So that's pretty close. I'm supposed to be seeing negative 1.5. That's pretty good. Let me see what it goes to when I turn the FM on. Whoa, check it out, guys. It goes up to 10.5, almost 11. So negative. So that is the 20 volts, or the 10 volts I'm supposed to be measuring across that capacitor when I do the measurement. That's really interesting. So when I did the alignment, you look for 10 volts across that when you're doing the alignment as part of the FM alignment. Okay, one more thing I want to check. Let's see if you can see it. According to this right here, that 7x7, that's that first driver tube. Of course, we checked that. We came pretty good. We did 125 volts. Now I want to look at that sort of bias voltage that's supposed to appear at pin 6. Okay, and that's there. It's easy to get to. It's real easy to get to. So right here is the that 7x7, and pin 6 is right here at the end of this little bias capacitor. So let me go ahead and check that. That's supposed to be negative 1.5, negative 1.3. It's kind of, so I'm seeing about negative 1.3 to negative 1.5. It kind of moves a little bit, but when I go up to FM, I see about negative 10. Okay, I think that changes with signal level coming in. I'm not sure because the static increased, so did that number. And I remember it said when you did the alignment to set the signal generator such that you have 10 volts minimum across that capacitor. So I don't know. I'm not going to worry about that right now. What I am going to worry about is getting that resistor mounted up so that we can dissipate that heat. If I do a little bit of basic math here and using Ohm's law, V equals IR, right, or P for power equals I squared R, and I measured the current, so I know the current, I got about 0.75 amps, and I know that's a 25 ohm resistor, so there you go, I got I squared R. I squared is about 0.6, about 0.56 something, times 25 is roughly 14 watts. So we should be well within the range of that resistor because it's capable of dissipating 25 watts. So 14 watts will be fine. But you do need to understand this thing is going to get toasty at 14 watts, okay? So don't think that just because it's easily within the capabilities of it that you're not gonna feel it if you grab hold of it. Okay, let's get to mounting this beast, eh? There's the finished installation, guys, of that power resistor. Remember, this thing is a 25 ohm, and I'll just tell you it's a 25 watt. The white you're seeing there is some silicone heat transfer paste. Basically, it's to help the chassis to behave as a heat sink for this thing, to pull as much heat away as possible. I mounted it away from anything that would be on the other side of the chassis that would be affected by that heat, so that's great. I insulated the termination of the wires to this thing with some shrink tube, and then I put, just for a good measure, I put a coating of liquid tape on there as well. Once that hardens up, this thing it'll be pretty, you'd have to really be trying to touch the conductor on this power resistor. Alright, let's come around the inside and take a look at it. So I just used some Nylock self-locking nuts, and I ran the wires, as you see, I ran the wires through a nice rubber grommet. So the way it works is the line cord comes in, goes to the fuse there on the side of the barrel. The other side of the fuse, it happens to be at the end. That's connected to the black wire that goes out to this power resistor. After the power resistor, it comes back through a little bit of twisty action there, and then heads off around the other side of the line cord till it comes over here to the safety caps. So that's all there is to it. No big deal, no sweat. The most difficult challenge about these is mounting them, and that's not hard. I did scuff up the surface a little bit so it would be a better heat conductor. You know, if there's any corrosion or whatever, that kind of inhibits heat conduction. I want to take as much heat away from this little thing as I can.
Okie dokie, guys. I think we've solved a couple of problems this time around. Some of the alignment stuff is real grunt work, and it's hard to watch, I understand. And this power resistor thing is probably basic for a lot of you, but there are those folks who've asked me this in messages and stuff, so I thought it was important to kind of cover it a little bit. So I'm going to hit reassembling this thing here real soon. We're almost done with this set, believe it or not. It's been quite the slog, but we'll keep moving on it. And so I'm going to wrap it up for today. From your Western Outpost in Salt Lake City, this is Michael. That's all for now.